Hello everyone. Today we're going to be talking about one variable inequalities. And this should be a bit of a review for you from last year, but pay attention because there'll be a few new things as well. So first off, just for some notation, these are the 5 inequalities that we've got to deal with. Hopefully you've seen these before. This equal sign with a slash through it means is not equal to. This little symbol means is less than, or as I like to prefer thinking about it, I like to think of it as is to the left of. So we're talking about one variable inequalities, so all of these things are going to be taking place on the number line. One variable means one dimension, that means a line. So less than means to the left of on the number line. Similarly, this symbol means is greater than or is to the right of. When we take the is less than sign and we tack on a little half of an equal sign, then we have is less than or equal to. Or we take this symbol, the greater than one, and tack on a half of an equal sign. It means is greater than or equal to. And these are inclusive ors, meaning that either less than or equals is a good thing. These are strict inequalities, we call them, meaning we don't include where equality happens, whereas these ones we do include where equality happens. And we're really talking about sets here. Sets of points on the number line that satisfy whatever statement we're making with the inequality. So just to look at a couple of examples, we can graph inequalities on the number line pretty easily. So first example here will be x is less than or equal to 5. So we want to include in our set the point where x is actually equal to 5. That's, of course, the point 5 on the number line. And the way we show that we want to include the point is, when you do this set in red, is where some colored pencils or pens is going to help you out here. So we'll put a closed circle on the point we've named 5, meaning we do want to include it. And then we want everything to the left of that, because x is supposed to be to the left of 5 on the number line. So we're just going to shade the number line to the left of that point. I'll just put a little arrow here on the shading saying that we want everything to the left, going on forever and ever and ever in that direction. Sometimes I see people doing it above the line. That's totally fine. However you did it, as long as you're communicating the set clearly, that's fine. Depending on how you were shown to do it last year, I'm perfectly fine with any of that. So this, when we include this point, and this point is what we call the boundary point, and we have boundary points when we're on the number line, the boundary is going to change and be different things as we go up in dimensionality. But for right now, this is just going to be a point, which is the boundary. And my red's not showing up too well in the video, but that's okay. Hopefully you can read that. And when we include the boundary point, we call that a closed set. Including the boundary means a closed set. That means these two inequalities give rise to what are called closed sets that include the boundary. Now, if we use an inequality like this, the strictly greater than, here x is strictly greater than -2, well, now we don't want to include where equality happens. That's at the point -2. So we're going to use an open circle there to show that we don't want that point. But we do want every point, remember, to the right of -2. So we'll shade that in to the right, and showing that we want everything over here. Okay. We can't obviously put actual closed circles on every single point, well, because there's uncountably many points in there. So we'll just shade to the right. Here, we're not including the boundary point, so this is called an open set. Okay, so that's just the basics. Not too hard. I'm sure, hopefully you guys remember this from last year. And also, hopefully you remember how to solve one variable inequalities. It's going to be very much similar to solving equations. because of course solving just means to undo what's being done to a variable. So that's what we're going to do. Look at this example here. Negative 5x plus 4 is greater than 29, or is to the right of 29. Here we just look at what's being done to x, and we undo those things in reverse order of operations. Okay, so the first thing we got to get rid of is the addition, not the multiplication. We undo things in reverse order. So we get rid of this, or undo this adding 4 by subtracting 4. But of course we have to do that to both sides of the inequality. The whole point of doing that is that adding 4 and subtracting 4 cancel each other out. So now we're left with negative 5x is greater than 29 minus 4 is 25. Oops, excuse me. 25, not 29. Then we continue undoing. We undo a multiplication by negative 5 by dividing both sides by negative 5. Point being that this will cancel out. And now we have x is greater than 25 divided by negative 5 is, of course, negative 5. So this should be the solution to this inequality. Basically, this thing and this thing should be saying the exact same things. Okay. Now we can graph this inequality as well, just like we were doing before. Here's 0, here's negative 5. We don't want to include the boundary because it's a strict inequality, but we do want to include everything to the right of that boundary point. So here would be our solution set. And there's some set notation we could use here, but I'm not a stickler on it. We might talk about that in class, because one of the interesting things is that I've seen on the state tests that you'll be taking for algebra is that they actually write the set notation completely wrong, which I find somewhat hilarious. But we'll talk about that in class. But we can also check our solution here. And we want to check two things. First, we want to check the boundary, make sure we actually got that right. So we take where equality happens and plug it back in up here and see if equality happens up here. So we check the boundary point by asking ourselves, is negative 5 times negative 5 plus 4 actually equal to 29? And so we see negative 5 times negative 5, well, that becomes a positive 25. We're asking ourselves this question. Is that actually equal to 29? Yes, we did that. So that's checking the boundary. But we also want to check to see if we shaded to the correct direction. I think we probably did. And the way we're going to do that is we're just going to pick a point over here to the right of negative 5 and plug it back into the inequality. So an easy point to check would be 0. So if that's in your supposed solution set, great. The 0 is really easy to work with. So we also ask ourselves, is negative 5 times 0 plus 4, is that actually equal to, or excuse me, is that greater than 29? If it is, then we know we did it right. So here we go. Negative 5 times 0 is 0. Add 4 to 0. 4, is that greater than 29? Uh-oh. No, it's not. Meaning we did something wrong. That's a big question. What went wrong here? And hopefully some of you remember. But if not, or even if you did, let's just illustrate it for you really quick here. Big thing here is, let's take two easy numbers just to really get the idea here. Maybe 5 and 10. And how are 5 and 10 related? Well, 5 is certainly to the left of 10. Hopefully we can all agree on that. So let's think here. If we add something to both sides, we'll add 2 to both of them. 5 plus 2 is 7. 10 plus 2 is 12. 7 is definitely still less than 12. Okay, that's good. Let's take 5 and 10 again. This time let's subtract something. something like 2. 5 minus 2 is 3. 10 minus 2 is 8. Does this inequality still hold? Yes, 3 is still to the left of 8. Let's multiply by something. 5 and 10. We will maybe times 2. Oops, I meant to do that in red. Not a big deal. Times 2 times 2. Of course, 5 was still less than 10. After we multiply both sides by 2, 5 times 2 is 10. 10 times 2 is 20. Yes, 10 is still to the left of 20. Great. Let's divide by 2. 5 is less than 10. If we divide both sides by 2, and 5 divided by 2, 5 halves, or 2.5, either way you want to think about it. And 10 divided by 2 is 5. Does this inequality still hold? Yes. So 2.5 is still less than 5. Okay, all of those work fine. We have an inequality, we add something to both of them, the inequality still holds. We have an inequality, we subtract something from both of them, the inequality still holds. We multiply both of them by a number, inequality still holds. We divide both of them by a number, inequality still holds. However, we did not check one thing. Notice these are both positive numbers that we multiplied and divided by. Addition and subtraction doesn't really matter because subtraction is really just adding a negative. So, here's the thing. 5 is less than 10. If we multiply both of them by negative 2, five times negative 2 is negative 10. 10 times negative 2 is negative 20. Oops, negative 10 is definitely not to the left of negative 20. That's a big thing here. So if we have an inequality and we multiply both sides of that inequality by a negative number, the inequality here must be switched around. Similarly, 5 is certainly less than 10. If we divide both of them by negative 2, 5 divided by negative 2 is negative 2.5. 10 divided by negative 2 is negative 5. But now negative 2.5 is most definitely not to the left of negative 5. It's to the right of it. So again, if we divide both sides by a negative number, we have to flip the inequality around. And that's the only thing that's different for solving inequalities as opposed to equations. That's the only difference. Okay. So let's redo example 3 really quick here. We have our inequality. I'm going to undo what's being done to the variable x. So first we subtract 4 from both sides. Subtracting 4 doesn't flip the inequality, so everything's still fine. Negative 5x is now still going to be greater than 25. Now we divide both sides by negative 5. Now we should note that we're dividing by a negative number, so let's put a big square around this and put stars there to remind ourselves that yes, hey, we got to flip that thing, just so we don't forget it. Those things are going to cancel out. Now we have x on the left-hand side. 25 divided by negative 5 is negative 5. But now we're going to flip the inequality from greater than to less than. And that's our solution set, is every x value that is left of negative 5. We'll graph that. Here's 0, here's negative 5. We don't want to include where equality happens, so we'll show that with an open circle. I'm going to shade everything to the left. Okay. And now, we already checked where equality happens last time. So of course, negative 5 times negative 5, that's positive 25, plus 4, that's equal to 29. That's where our boundary should be. But now we'll check the actual direction of the shading, we'll pick something easy like, oh, I don't know, negative 10 is over in here, and powers of 10 are pretty easy to work with. So is it true that negative 5 times negative 10 plus 4, is that greater than 29? Well, negative 5 times negative 10, that's a positive 50, plus 4. Is that greater than 29? Well, yeah, of course, 54 is greater than 29. We did it correctly. Fantastic. And so, be ready to do some practice problems when we get to class next time. We'll check to see if you watched that way. Thanks for watching.